Hi, here we are jumping back into Chapter 4, and this is the second lecture for Chapter 4. And what we're going to be doing from here, just to kind of give you an outline, is we're going to talk about 5 types of reactions. So one being this reaction called precipitation reactions. Second, we'll talk about acid-base reactions. You don't even need to write this, it's just kind of going to give you an outline. Gas formation, gas-forming reactions, displacement reactions, and then lastly, oxidation reduction. Okay, so that gives you an overview of what's to come in this chapter. So here, I'm going to go ahead and label this one as number 1, just to kind of keep you organized, because my numbers don't go like that for the outline. So first, let's focus on these things called precipitation reactions, okay? So for precipitation reactions, we've actually already seen these back a couple of chapters ago when we talked about double replacement reactions. It's going to look really similar to those. It's just kind of a subset, okay? What's happening here with precipitation, and they're also called metathesis reactions, so you're going to have a lab assignment on this type of reaction. The definition here is you start with 2 ionic compounds, which can be called soluble salts. All it means is salt stands for ionic compound. Soluble means it's dissolved in water. So one soluble salt, another soluble salt, both aqueous, meaning dissolved in water. And when you pour 2 things together and you get a solid insoluble salt, which means you're an ionic compound, but you don't dissolve. Okay, so what that would look like is a solid at the bottom of the beaker, right? You would produce a solid. It's very uncommon for this to happen at home. Like if you like to maybe mix a juice with a soda or something, if you mix them, you don't normally see a solid form, right? That would be weird. But here what's happening is you're taking 2 solutions, the ions are rearranging, and you're making a solid. That is called a precipitate. Okay, so a precipitate is produced, and that's a solid product there. So here we have to use what are called solubility rules. So one of the handouts for this chapter that I mentioned earlier is here. It includes what are called the solubility rules. What it's going to tell you is which ionic compounds dissolve and which don't. Remember earlier in the chapter I told you in general ionic compounds are very soluble, but there are some exceptions, okay? So here is going to be how you determine this. You only have to memorize the ones in red, and I'll explain. At the top portion of this sheet, these are the soluble ions. These are ions that make a compound soluble. For example, any compound with lithium, lithium chloride, lithium phosphate, lithium fluoride, lithium nitrate. If there is lithium present, you are soluble, no exceptions. See that? Sodium, soluble, no exceptions. So these red ones right here are really important because in general, we say that if they are in an ionic compound, they make the compound soluble. There may be a couple of exceptions here listed, but the ones in red, we are going to generally automatically say those compounds are soluble, okay, on a test. Whereas, look at chloride here. Here's how you read this. This column is called the rule. This column is called the exceptions. So chloride. If there's a chloride in the compound, you are most likely soluble. Do you see that? That's the rule. Unless chlorine is with silver. So if it's silver chloride, it doesn't follow the chlorine rule. Instead, it actually is insoluble. It would make a white solid in your beaker. Same with mercury chloride. The presence of mercury makes it insoluble. Lead chloride, insoluble. So if you're insoluble, you are going to be a solid precipitate. Down here at the bottom of this page, it's the opposite. These ions right here generally make you insoluble, meaning you're normally a solid. So like here, let me say this too. If you're soluble, that means you're going to be aqueous. I would write a little AQ here. Soluble means you're going to be aqueous. You're going to dissolve. If you're insoluble, you're going to be a little S for solid, okay? Because you're not going to dissolve. So if you have sulfide in your compound, you are likely insoluble. You're probably going to be a solid. unless you're with ammonium or the alkali metal cations. So you know these red ones right here that make everybody soluble? So that's what this is listing. If sulfide is normally insoluble, but if it's with ammonium, see how it's an exception? That's going to make it soluble. So same with all of these. Carbonate usually is insoluble unless it's with ammonium or an alkali metal cation from group 1. You don't have to memorize this list, we just need to know how to use it. So I'll come back to that as we do examples, okay? So here, these are the ones that I want you to memorize. Group 1A makes you automatically soluble: ammonium, nitrate, and acetate. Those make any compound soluble. It's just going to make your life a lot easier and faster here. Classify each as soluble or not. Okay, look at sodium carbonate. Do you see that you have a group 1 metal? If you have a group 1 metal, you are automatically soluble. So he would be an aqueous compound. If you went in water, he would dissolve. Lead 2 sulfate. Okay, well, none of these apply. It's not a group 1 metal, and I don't see sulfate. So let's go to our rules. We're going to look for lead and sulfate. Do you see that you don't see lead on a rule? You don't start with the exception. You start with the rule. There's no lead, but there is a sulfate rule. So let's start with that. Sulfate is typically soluble, yes? Okay, so sulfate wants to be soluble unless it's with one of these. Well, do you see that it's with lead, which is an exception? So it does not follow its rule soluble. It actually will be insoluble. So here we would say this guy is insoluble. So what would he produce in a solution? Would he be aqueous? No, he would actually be a solid. He would be a solid precipitate, or a solid if you put him in water. Okay, think about these. Cobalt 2 hydroxide. So cobalt 2 hydroxide. Remember our flip-flop rule from a couple chapters ago. Okay, cobalt, he is not in a rule, but hydroxide is. Hydroxide is usually insoluble. He will not normally dissolve. Here he's with cobalt. Well, cobalt is not listed, so that means he follows his rule. Since he's following his rule, that means he is an insoluble compound. So he's insoluble, which means, will he be aqueous or will he be solid? He will be a solid. Does that make sense? So even though he's an ionic compound and most dissolve, there are some that don't, and this is an example. Barium nitrate, okay? Well, if you memorize these quick little ones right here, it'll be an easy answer because nitrate makes anything and everything soluble. So he's automatically soluble, which means he would be aqueous. Ammonium phosphate. Ammonium is also one of these that automatically soluble. And if you're wondering or want to see kind of proof of this too, if you go down here to phosphate, he is normally insoluble, you're right. He's usually a solid, but he's with ammonium. So he doesn't follow his normal rule. He actually has an exception, and he is soluble, just like we already predicted. And so he also will be aqueous. But knowing these by memory just keeps you from having to go to the solubility rule list, okay? So let's see how to further use these solubility rules to predict reactions. So what this is going to look like. For a double, it's the same as a double replacement. You see how you have two compounds, AB plus CD, and both are aqueous. I should have written that. They're both soluble in water. A and D are going to come together, and then C and B are going to come together. You're just exchanging ions. If you are a precipitation reaction, one of these two will be a solid, okay? If they're both aqueous, nothing happened. It's no reaction. But if one of these becomes a solid based on solubility rules, then you have a precipitation reaction. So one of them has to be a solid in order to be precipitation. So we'll see how to do this. So will a precipitate form when solutions of barium nitrate and KOH are mixed? The first thing you're going to need to do is identify their charges. So what you're working with here is barium plus 2 and nitrate, NO3 minus 1. You're not really concerned with how many ions there are. I just want to know their correct charge. Ba plus 2, nitrate NO3 minus 1. On that handout, I put the polyatomics so that you could have them handy for yourself, but they are in red because you do need to memorize them. So here are the polyatomic ions, and you can have them handy, but do start memorizing them again as you're working. And then here, K is a plus 1, and hydroxide is a minus 1. So does it make sense that we will flip-flop who goes with who? So barium's positive, so he'll come together with hydroxide. So one of your products is going to be BaOH2. See how I did the flip-flop? The 1 came down and the 2 came down. That's one product. The other product will be K and NO3 coming together. Remember, the cation always goes first? So we'll put K first. K and NO3. It's a plus 1, minus 1, so the 1s come down. So these are our two products. That's step 1 always. So find the charges, flip-flop them, exchange the ions. Now we go to the solubility rules. So let's go look up barium hydroxide on here. Here's hydroxide. He normally is insoluble unless he's with barium. Do you see that this time hydroxide would be insoluble, but he's with barium, so he's going to be soluble. So he actually will be soluble. He will be aqueous. So far we do not have a solid. Next, we look at K and NO3. Do you remember that K and NO3, they actually both, are ions that make everything soluble. So automatically soluble, aqueous. So will a precipitate form? In other words, will you get a solid product? No. So no reaction will occur there. All that you're doing is just mixing ions in a solution, and they're just still hanging out as ions. Let's do this one. So take a minute, break apart these compounds into their pieces. So think what ions are there, and then we flip-flop them. So see what you get there. Take a minute. Okay, so if we break these apart, sulfate is on your polyatomic sheet. He's SO4 minus 2. Okay, that's always his charge. You see how there's 3 of them? I'll remind you quickly how to do this. If there's 3 of them, do you see how that's a -6 charge? Which means we have to have a +6 charge. There's 2 irons. So if there's 2 irons, each one needs to be +3. So in this scenario, Fe is +3 and SO4 is -2. Okay, on the other, lithium hydroxide, lithium is always +1 from the periodic table, and hydroxide is always -1. So first you have to identify what ions are present, okay, and make sure to get their charges correct. Next, you do the flip-flop. So you allow who to go with who is kind of your next question. Fe is going to come together with OH. See how you're going to flip-flop the charges? So you're going to get FeOH3. That's going to be one possible product. The second possible product is going to be lithium and sulfate, Li2SO4. Now what do you do? So that's the hard part. That's the part of coming up with charges, flip-flopping everybody, getting who your products are. Then you go to your solubility rules. Iron 3 hydroxide. Hydroxide is normally insoluble. Iron is not listed here as an exception. So he follows his rule. He is insoluble, so he will be a solid. Yay! We actually did something here. We made a product. Something happened. Lithium makes everything soluble, so this is going to be aqueous. You should never get 2 solid products, but you also always should check yourself, okay? So here, will a precipitation reaction happen? Yes. And who will it be? FeOH3. Okay? Now let's see how to write these actual full-out reactions, okay? So here there's there's 3 ways of writing metathesis reactions. Remember, that's just a fancy word for a precipitation reaction where you're taking 2 aqueous and you're making a solid. So the 3 ways are called molecular, complete ionic, and net ionic. Molecular is what we've been working with in the past couple of chapters, all right, where we write out a reaction and we balance it, and there's nothing much more to it. It just shows who do you start with, who do you end with, and then balance with coefficients. The complete ionic actually shows what do these substances look like in water. Are they together, intact, or are they apart as ions? So here you see how it tells me AgNO3 is aqueous? That means he is soluble, so he's dissolved in water. He's an ionic compound. Remember, if you're an ionic compound and you dissolve, you are a strong electrolyte. So you see how it's showing the 2 ions? Because that's in reality what he looks like in solution. Same for KCl. He's aqueous and he's ionic, which means he's a strong electrolyte. He also breaks apart. Do you see how it's just giving us a clearer picture of what is in the beaker? He's floating, he's floating, he's floating, he's floating. Now, when you mix the 2 components, you see how you make a solid? Well, once you're a solid, that means you are bound together. You are not going to break apart anymore, right? So here is your solid precipitate. We're not breaking him apart because he is stuck together as a clump. Do you get what I mean? The other product is KNO3, who's aqueous and ionic. So he breaks apart into his individual ions. So you see how the complete ionic is showing every ion, every compound, and indicating whether it's broken apart or whether it's together. Here what you're going to do is you're going to break apart all strong electrolytes when you're writing one of these. But what you're going to keep together here is you're going to keep together any solids, liquids, gases, and weak acids and bases. So what you're going to keep together here, and I'll just mention this, keep together. Solids, liquids, gases, and then anything that is a weak or non-electrolyte. We'll keep doing this as we go. So if you're aqueous and you're an ionic compound, you break apart. If you're a solid, liquid, or gas, you stay together. And if you're a weak or non-electrolyte, you stay together, okay? The net ionic is the shortest, and it's just the most, the smallest of the reactions. What it's doing is it is showing you what is actually happening here. You're giving me all these ions, blah, 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 but what's actually changing? Well, if you look up here in the complete ionic, you'll notice that a couple of guys stay exactly the same. You see how nitrate was an ion and he's still an ion? He is what's called a spectator ion because he didn't do anything. He just spectated. So we actually leave him out of the net ionic because he's not exciting. He didn't do anything. Okay, he just sat there. Same with the K+. See how he's still an ion? So he's a spectator ion. But look at the other guys. The other guys actually did something. Look, silver was alone, chloride was alone, and now they're in a clump together. So that's why the net ionic only includes these components because that's who's actually changing. And you leave out spectator ions. So let's do some practice here. Okay, here is where this says the same thing that I put up here in the margin there. You break apart strong electrolytes, you leave together weak acids, and you leave together anything solid, liquid, or gas, okay? So here, let's do an example. This is going to put everything together that we've talked about so far. Okay, so here we've got barium chloride and potassium sulfate. So our first thing we need to do is figure out their charges. So barium is always a +2. Chloride is always a -1. Remember, I don't care how many there are of things. I just want to know their charges. Here you've got K+, and sulfate. And for a while, keep the polyatomic list handy. Don't let the memory be hard at first, okay? And then you flip-flop. So who's going to go together? The barium and the sulfate. You see how it's a +2 and a -2? So +2 and -2 means they're going to cancel out. So one of your products is going to be BaSO4. Your other product will be K and Cl together. They're a +1 and a -1. So we will predict them to be KCl. Okay, that's the hardest part, I think. The next step is to go to your solubility rules and decide if either of these will, well, either one, see if they are soluble or insoluble. So barium sulfate. Okay, here's sulfate. He's normally soluble unless he's with barium. See how barium's on the list? So sulfate is not soluble, he's insoluble, which means he is a solid. Because he is insoluble, he's a solid. He is now clumped together at the bottom of the beaker. Potassium, however, makes all compounds soluble, so this will be aqueous. Okay, so did a reaction occur? Yes. And did we make a precipitate? Yes. Now, we also need to balance this. Remember how I told you don't worry about how many of the things there are? But now you care about that. You see how there's 2 chlorines on the left? So I'm going to put a big 2. Remember, you add coefficients to balance. So 2 chlorides and 2 Ks. See how that did that? And it actually fixed the issue. 2 Ks, 2 Cls, 1 barium, 1 barium, 1 sulfate, 1 sulfate. So I just balanced it using coefficients. Now, the rest is kind of easier because you just did the hard work. The complete ionic is going to include everybody, right? So, 1 barium, aqueous ion. Does that make sense? Because he is floating around as an ion. Chloride, floating around as an ion. Potassium, floating around as an ion. And sulfate. Now let's look and see if we have the right number. So here, when we're writing the ionic, we do care how many ions are floating. Do you see that there was only 1 barium floating around, but that there were 2 chlorines? So I'm going to put a big 2 here to say there were 2 chlorides in solution. You see where I'm getting that from? Right here. Okay, there's also 2 potassiums to start with, right? And only 1 sulfate. You feel good about that so far? So what we did was we showed the ions with their correct charges, and then we indicated how many were present. Now the products, remember, a solid you keep together because that is what he looks like. So BaSO4 is a solid. Then this guy, he's aqueous and he's ionic, which means he's a strong electrolyte. We're going to break him apart. What we need to see here is that we have 2 K pluses floating and 2 chlorides floating. So when you're putting the amounts, you have to pay attention both to how many are in the compound and how many compounds are present. You see how that's what the coefficient is telling you? Because what this is doing is it's giving us a big picture of how many of everybody is there. What do they look like? Are they an ion? Are they a compound? Okay, so that's the complete ionic. Then if you X out anything that looks the same on both sides, or I'll underline them. You see how there's 2 chlorides right here, aqueous, 2 chlorides, aqueous? Those are spectator ions. 2 K pluses and 2 K pluses. Okay, those guys didn't do anything. However, look at the others. Look at barium. He was alone. Sulfate was alone, but now they're in a clump. That's where your net ionic is coming into play. There's 1 barium who was aqueous. There was 1 sulfate who was aqueous, and they came together to form 1 compound. It should balance out perfectly for you if you've done the other steps correctly. The net ionic is just the take-home, the cliff notes. It's what actually happened in the reaction. Here's the deal. If you get 2 aqueous products, that means nothing happened. So you actually don't have to write the complete or net ionic because there's nothing to show. Okay? You only write these if you've actually produced something new. Okay? You've produced a solid, a liquid, a gas, etc. Right now we're only talking about solids because we're talking precipitation. So let's try this again, giving you a chance to work through it on your own a little bit. So take a minute, look at these two compounds that are both aqueous, break them apart and pay attention to charges, and try to predict your two products right here. So you can, of course, pause the video if you need more time. Here I'll start writing out who we have. Ag plus 1 and NO3 minus 1. Barium plus 2 and chloride minus 1. Remember, you're not concerned right now about how many of everybody there is. Just who are they and what are their charges? Then you flip-flop. So silver and chlorine are going to come together to make AgCl. And barium and nitrate are going to come together to make BaNO3, 2. I do care about the number just from a flip-flop standpoint. Take the charges, flip-flop them so that we have balanced ionic compounds. Okay, that's our first step. The next step is to go to your solubility rules. So if we go to chloride, he's normally soluble but not with silver. So he's going to be insoluble. He's a solid. Barium nitrate, nitrate makes everything soluble. So he's aqueous. Now we need to remember to balance the equation. There's one silver, one nitrate, two nitrates. So I'm going to have to put a 2 here to get 2 nitrates, which just changed silver to 2, so I'm going to put a 2 there. 2 silver, 2 nitrate, 1 barium. So now, we predicted products, we predicted their states of matter, the solid and aqueous, and then we balanced it with coefficients. Now, the complete ionic, remember we're showing all the parts and the numbers, so do you see that there are 2 Ag plus 1? So I would encourage you to pause at any point and try this on your own before seeing me get through it. And then 2 nitrate ions. Okay, that's the first compound. There were 2 of each ion. And then a barium and a chloride. There's 2 chlorides if you'll notice. Watch that. See how there's 2 right here? Okay, keep a solid together, so 2 AgCl. And then break apart barium nitrate. 1 barium and 2 nitrates. And there is our complete ionic. So make sure you match in numbers of everything. And then we'll identify who the spectators are. Well, the nitrate didn't change, and the bariums didn't change. So those get left out, and the net ionic is just who actually changed. So silver plus 2 chloride goes to 2 AgCl. It is balanced, but what you'll notice is we do want to, this won't happen a ton, but you do want to simplify when possible. So you see how these all have a 2 in front of them? We would ideally leave those 2's out, because we want to show it in the simplest ratio. 1 silver, 1 chloride makes 1 silver chloride. Okay? All right, so I would pause your video and work through this next one, and then follow up with me and see how we compare. So here we have an SO4 minus 2. There are 3 of them. So that gives us a minus 6, which means we need a plus 6. So each of the irons here are going to be plus 3. Okay? So the Fe will be plus 3. Lithium plus 1 and hydroxide minus 1. So then we take the positive and negative together. So we're going to get FeOH3 and lithium sulfate. Okay, so take a second, see if you agree with that. See if you can tell what I did. I took the positive, negatives, flip-flopped them. Then go to solubility rules. Well, lithium makes everything soluble, so that's aqueous. Let's go check iron hydroxide. Iron 3 hydroxide. Okay, hydroxide's down here. He's normally insoluble. Iron is not an exception, so he is a solid. And then if you recall, the next step is to balance it. So now we care about number of things. So you see how there's 2 irons on the left? I'm going to try a 2 here. 2 irons, 2 irons. There's 3 sulfates. I also noticed that I put these here. I didn't need those. Okay. There's 3 sulfates. So you see I'm going to have to put a 3 here. 3 sulfates. That looks good. 2 irons, 2 irons. There's 6 lithium, so I might need to put a 6 here and see how that goes. 6 lithiums and 6 hydroxides, which actually works. 2 times 3 is 6. So there's my balanced equation. Now complete ionic, we're going to write everybody out, all the individual pieces. So keep up with how many and their charges. So 2Fe plus 3. See if you can tell where I got all that from. Fe had a plus 3 charge, and there's 2 of them because of the subscript. There are 3 sulfates that were floating around. Make sure to indicate the charge. There are 6 lithiums. There are 6 hydroxides. Okay, there are all of our reactants. So we care about number, charge, state. Number, charge, state. You got to show all 3. And then our product, okay, well, we keep our solid together. There's 2 FeOH3s that form. That's a solid. And then, let's see here, there's an aqueous ionic compound, so we're breaking him apart. Do you see that there's 6 lithiums? And there are 3 sulfates. That's all the pieces. Then we can go identify the spectators. Sulfate, sulfate, lithium, lithium. So those are not exciting. That's what I'm like at a sporting event. I'm a spectator. So I'm just sitting, nobody wants to watch me on TV. So what's left is the active players, right? So the non-ionic says 2 Fe plus 3s. They actually did something. Plus 6 hydroxides. They actually did something. To form 2 FeOH3. And then you think, can we simplify it? Remember, we just want to double check the coefficients. The coefficients can be simplified because 2, 6, and 2. So a 1, a 3, and a 1. And then that's where we are. Okay, so that is the part on precipitation reactions. So I'll stop there and I'll pick back up in the next video on acid-base reactions.